Hello everyone, this is lecture 5 of week 8. So, in the previous lectures of this week we learnt in detail about augmented Lagrangian method. We learnt the algorithm stepwise for when you have only equality constraints, and then we learnt the algorithm stepwise when we have both equality and inequality constraints, and we saw quite a few examples. So, in the previous lecture we saw a practical example, where it was the consumer utility maximization problem, and towards the end I mentioned that both of these methods, quadratic penalty method and augmented Lagrangian method, will be used only for nonlinear programming problem and not for linear programming problem. So, why is that the case, right? So, we will discuss that in this lecture, right. So, we will first start with an example. So, if you see the examples that we have worked out, right. So, so if you see this particular example, this particular example, you can see that the constraints are linear, but the objective function is nonlinear. So, I can take the same example, but change the objective function to a linear objective function. If I do that, then I would clearly have a linear programming problem, right. In a similar way, if you see this problem, the consumer utility maximization problem, you can see that the constraints here are linear as well, right. So, just the objective function is non-linear. So, if I modify the objective function to be linear, we will have a linear programming problem, right. So, I will do that for this particular problem, where we have the triangle with vertices 0 0 1 0 and half half as the constraint set. So, instead of minimizing the distance from the point 3 comma 2 to the feasible set, so we will write down a linear objective function. So, here I am going to write down the objective function to be minus x2, okay. That is, I am going to maximize x2 subject to the condition that the feasible set is this triangle whatever we have mentioned here, right. So, just by looking at the figure, you can figure out that if you want to maximize x2, the answer is half, right. So, because there is a vertex at half comma half, right. So, so if I write down the following problem, that is, if I write down this problem, minimize minus x2. So, maximize x2 is just minimize minus x2, right, subject to the same set of conditions, minus x1 plus x2 less than or equal to 0, x1 plus x2 minus 1 less than or equal to 0, and minus x2 less than or equal to 0, right. So, the answer is minus half. So, since you are minimizing minus x2, so the answer is going to be minus half, right. So, let us check if I give this particular problem to the code that we already have, right. So, we have already written the codes for augmented Lagrangian methods for various constraints. When we have this particular constraint set, we have already written down the code, right. So, let us actually use that particular code and check if the code gives us the right answer, right. Okay. So, this is augmented Lagrangian method for utility maximization. This is the problem where we minimized half of x naught minus 3 the whole squared plus x1 minus 2 the whole squared, with subject to the feasible set being the triangle, right. So, I am just going to change f of x, right, to minus x of 1, right. So, I want to retain this problem, that is why I am commenting out instead of removing it, okay. And similarly here, so I will use this I mean I will comment this out and write a new line of code, right. Again that is to retain the code that is already there. Okay. So, yeah, if f of x is minus x of 1, then the gradient will be 0 comma minus 1, and yeah, for Hessian we just have to remove this. Okay. So, yeah, I have just commented out np dot of I of 2 behind this. Okay. All right, and so yeah, let us choose the initial point to be 3 comma 2, right. So, that is some point outside, and yeah, let us choose mu to be 0 0 0 as we usually choose, right, and let us check what is happening to this code. I mean does it give the right answer or not. Okay. So, yeah, it says an error saying that we have got a singular matrix as the Hessian, right. So, the Hessian that we have here is the code says that we are having singular matrix, right. So, in such a case we usually try to change the value of x, right. So, 3 comma 2 is a point that is not feasible, right. So, you can see that if you recall the feasible set, yeah, this is the feasible set. So, 3 comma 2 is somewhere outside, right. So, that is why we are actually finding the distance between 3 comma 2 to this feasible set, right. So, let us try giving a feasible point. Okay. So, let us say I give half comma 0, right. So, okay, so let us see what happens. The same error, it says singular matrix again. Okay. So, let us try changing the value of mu from 0 0 0 to 1 1 1. Okay. Again I am getting the same issue, it is saying that I am having a singular matrix, right. So, let us try a point much outside. So, yeah, I am going to try a point in the negative axis of x1 and x2. So, that is certainly not there in the feasible set. So, let me give minus 2 minus 1, okay, and let us check what happens now. Okay. So, of course, you can see that it says singular matrix again, but what you can see is that there is one step that has passed. Okay. So, we have come to a different point. So, the first at the first point minus 2 minus 1, the matrix was not singular, the Hessian matrix was not singular, right, but at the next point, that is 1.5 comma 1, the matrix has actually become singular, right. So, what this tells us is that for most of the points it appears that the Hessian matrix is singular, right, but possibly there are certain points where it is not singular. That is certainly a problem, because if I have to search for the right point everywhere, and even then I mean we have not got the answer, right, because I somehow found a point when the Hessian is non-singular, right, but I mean when the trajectory moved to another point, say 1.5 comma 1, the matrix has again become singular, right. So, that is not good either, right, because until I reach the answer, at every point I need to have the Hessian matrix to be non-singular, otherwise I mean I cannot proceed with this matrix, right. So, why is this happening? Is there a problem in the sense, is there a result which says that the Hessian matrix is singular in many of the places if the problem is a linear programming problem, right. So, yeah, we will discuss about that. Okay. So, let us consider a general linear programming problem. So, if you recall, I mean much earlier we actually gave the general structure, right. So, this is the general structure of a linear programming problem, where the objective function as well as the inequality constraints as well as the equality constraints are linear, right. So, if you yeah, so I will write down this problem, and we will discuss how it can be modified, right. So, we have this particular problem where we are minimizing C transpose x subject to A transpose x minus B I less than or equal to 0 for all I in 1 to P, and A bar transpose x minus B I bar equal to 0 for all, sorry, I will write as j equal to 1 to m. Okay. So, if I put all these P constraints together, so I can write this as, the objective function remains the same, but this first line, that is the set of all inequality constraints, I can write them as Ax minus B less than or equal to 0. Okay. So, where okay, I will come to that, and the line at the bottom, that is the m equality constraints, I can actually write it as A bar x minus B bar equal to 0. Okay. Where A is a P cross n matrix, right. So, the first row of A will have A1 transpose, second row will have A2 transpose dot dot dot, the ith row will have AI transpose. So, you have P rows in all, so you have A to be a P cross n matrix, X is the same n cross 1 matrix, and B is a P cross 1 matrix. Okay, that will have B1, B2 dot 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 BP. Okay. In a similar way, I can write down the equality constraints where A bar is an m cross n matrix, X is an n cross 1 matrix, and B bar is an m cross 1 matrix, right. So, I have written I mean all of these constraints in the form of matrix inequalities and equality, right. So, that you can do it for any linear programming problem or any constraint set that is defined as defined using linear constraints. Okay. All right. So, now let us actually analyze what happens to the Hessian of the augmented Lagrangian function, okay, when we are actually working with a linear programming problem. Okay. So, fine, I mean you can, I mean I will so we have the expression for the Hessian of the augmented Lagrangian function here, right. So, note that since f is an objective function and that is linear, so the Hessian is 0. Height j's are linear constraints, so their Hessians are also 0. So, this will go to 0, and similarly here as well it will go to 0, but this will stay, del height j transpose will stay. Okay. In a similar way, del gi is 0 because gi has gi is inequality constraints and they are also linear, right. So, the Hessian of gi will be 0. Okay. And del gi transpose will, I mean that need not be 0 because it just has the gradient, right. So, what it means is that the Hessian will only have this particular term del height j of x transpose, and this the indicator of j of x plus mu I by 2 gamma greater than or equal to 0 into del j of x plus del j of x transpose. Okay. So, let me write that down. So, for a linear programming problem, the Hessian of the augmented Lagrangian function is just 2 gamma into summation del height j of x transpose, where j equal to 1 to m, plus summation I equal to 1 to p j of x plus mu I by 2 gamma greater than or equal to 0 del j of x transpose. Okay. So, the Hessian becomes simplified this way if you have a linear programming problem, right. So, let us actually consider the case when you have only equality constraints in the linear program. Okay. So, case 1 where the problem is min C transpose x subject to A bar x equal to B bar, okay, just A bar x equal to B bar. Okay. So, in that case you do not have the del gi component, right. So, that becomes 0, but now there is something that you need to have a look at. So, what is del H1? Del H1 is just A1 bar, right. So, the first constraint you can recall is that say A1 bar transpose X equal to B1 bar, right. So, if you take the gradient, it is just A1 bar, right, and for the second constraint it is A2 bar, for the third constraint it is A3 bar dot dot dot, for the mth constraint it is AM bar, right. So, this whole summation that you have here, summation del H j of x into del H j of x transpose, right, that can be written as, so 2 gamma is outside anyway, it can be written as A bar into A bar transpose. Okay. So, it is just product of the matrices A bar and A bar transpose, right, and so we are checking whether this matrix is invertible or not, right. So, basic linear algebra should tell you that A bar, you can recall that it is an m cross n matrix. So, A bar transpose is an n is an m cross m matrix, right. Let me verify if I am saying this correct. So, yeah, this has to be A bar transpose A bar, let me correct that. So, yeah, so that is because yeah, so I told you that the first column is going to be A1 bar, right. So, and the second column is going to be A2 bar. So, note that A1 bar is an n dimensional vector, similarly A2 any AJ bar is an n dimensional vector, you have m of them, right. So, you have m column vectors each of size n, right. So, that is an n cross m matrix. So, n cross m matrix is actually A bar transpose, right. So, yeah, that is please correct this. So, it is A bar transpose A bar, right. So, A bar transpose A bar is actually an n cross n matrix, because A bar transpose is n cross m, this is m cross n. So, A bar transpose A bar is actually an n cross n matrix, okay. And when would this be non-singular? So, it would be non-singular if the rank of A bar transpose A is equal to n, okay. And basic linear algebra should tell you that that would happen if the rank of A bar is equal to n, okay. If the rank of A bar is equal to n, then we will have A bar transpose A bar as a non-singular matrix, or I mean the rank of A bar transpose A bar will be equal to n, and thus it will be a non-singular matrix, okay. So, I can write that down. So, A bar transpose A bar is non-singular if and only if rank of A bar transpose A bar equal to n, which in turn happens if and only if rank of A bar equal to n, okay. So, but when would rank of A bar be equal to n? So, the first thing is that m has to be greater than or equal to n, right. So, if m is less than n, then there is no way that the rank of A bar is going to be equal to n, right. So, I mean rank is actually less than or equal to the number of rows as well as the number of columns. So, if m is less than n, then rank of A bar is less than or equal to m, which is strictly less than n, right. So, that is not going to happen. So, if the number of equality constraints that you have here is less than n, so this is never going to happen, okay. The rank of A bar is never going to be n, okay, fine. So, yeah, if m is greater than or equal to n, we may have rank of A bar equal to n. So, but there is a problem with that as well. Why is that? Because suppose, yeah, you have an A bar matrix with rank n, okay. So, then you know that the set of solutions for A bar x equal to b is a singleton set, okay. So, rank of A bar equal to n implies that the set of X for which A bar X equal to B happens to be a singleton set. Okay. So, what does this tell you? If you take this particular problem, right, you either have rank of A bar less than n, in that case the Hessian is going to be singular, right. If in our good fortune we have rank of A bar is equal to n, then we do not have to struggle so much by working out the augmented Lagrangian method. We already have the answer, because A bar X equal to B has only a unique solution, right. So, that is going to be the answer, right. So, if you have a unique solution, then that is the answer. You do not you do not need to process the problem any further, right. So, what this tells us is that either the problem is trivial when rank of A bar is equal to n, or when rank of A bar is less than n, the Hessian is non singular, which means you cannot use this particular method. Okay. So, that is what happens when you have only equality constraints. Okay. So, now what happens when you have inequality constraints? So, fine, this is the special case when you have only equality constraints. So, the next question is what happens when you have inequality constraints as well, right. So, let us check that too. Okay. So, let me consider the case when you have only inequality constraints, where you have, so that is Ax less than or equal to B. Okay. Okay. So, in this case, you do not have equality constraints. So, this del Hij transpose goes to 0, but so you only have del Gi transpose, and del Gi will turn out to be A transpose, right. So, so here as well, writing down the Hessian of L gamma is simple. It is just 2 gamma into, so you have this. So, let me not write it as A transpose A, but I will write this as summation I equal to 1 to P, the indicator function of Gi of x plus mu I by 2 gamma greater than or equal to 0 into AI transpose AI, AI transpose. AI is a column vector. So, the column vector into the row vector becomes a matrix, right. So that is what happens. So, you have this particular matrix as the Hessian matrix. Okay. So, here again you have all these things whatever I have written down here. So, you might be confused as to how to handle this indicator function. Okay. So, what this indicator function says is very simple. Okay. Unless you satisfy this particular constraint, okay, which is, so Gi of x is just A transpose x minus Bi, right. So, you can write that if that is, that is looking simpler. Okay. So, it is AI transpose x minus Bi plus mu I by 2 gamma greater than or equal to 0. Okay. So, if it turns out that the constraint, particular constraint, let us say AI transpose x minus Bi is greater than 0, okay, that is you have an x where a particular constraint is not satisfied. Okay. In such a case, this matrix will certainly exist, AI transpose will exist. Okay. Otherwise, so if it turns out that AI transpose x minus Bi plus mu I by 2 gamma is less than 0, okay, this AI transpose will not exist. Okay. So, it is like removing certain columns in A. Okay. So, it is not completely A into A bar, A into A transpose, right, or sorry, A transpose into A, I am sorry. The result of this particular summation whatever you have here, right, it is not exactly A transpose A, but you take only specific columns of A transpose, right, and if you can call it B if you want to. Okay. So, and do the transpose, right. So, the product of those two matrices is what you will actually get as the Hessian here. Okay. So, just as an example, okay, I mean since if you are not getting this. So, yeah, here is a problem that you have with only inequality constraints, right. So, let us say for so I mean if you write it in this form Ax minus b less than or equal to 0, right. So, you will have minus 1 1, okay. So, that is A1, right. So, A1 is minus 1 comma 1, A2 is 1 comma 1 and A3 is 0 comma minus 1, right. So, minus x1 plus x2 is x1 plus x2 and this is minus x2, okay. So, yeah, this is A1 transpose, A2 transpose and A3 transpose, right. So, yeah, if you construct a matrix with all of these A1, A2 and A3, so you will have the matrix A as this minus 1 1 1 1 and 0 minus 1, right, and of course A transpose is the reverse, you have minus 1 1 0 and 1 1 minus 1, right. So, now consider the particular point, let us say x is equal to 3 comma 2, okay, and let us say mu is all 0 0 0 for an example, okay. So, now let us check what happens to the Hessian matrix that we have defined here, right, below the last line, right. So, we will have del 2 L gamma of x lambda mu is 2 gamma into indicator function of yeah, so I will write this as A transpose x minus bi plus mu I by 2 gamma greater than or equal to 0 ai transpose, right, equal to 1 to 3 in this case because we have only p equal to 3, right. So, let us check the first constraint, is this does this hold. If you put, yeah, I will write down the values of bi's here. So, we will have b1 equal to 0, b2 equal to 1 and b3 equal to 0, right. So, that is because, yeah, so I have just written down the right hand side. So, this is 0 and here you have x1 plus x2 less than or equal to 1 and minus x2 less than or equal to 0, right. So, yeah, now if we try to check if so mu i's are all 0. So, you have A1 transpose x minus B1 is minus 3 plus 2. So, that is minus 1 plus 0 minus 0. So, it is minus 1 is less than 0. So, what happens is the first when I equal to 1, this is actually 0, okay. Now, for the second column you have A2 transpose x minus B2, that is 3 plus 2 5, 5 minus 1 is 4. So, 4 is greater than or equal to 0. So, you will have A2 transpose, right, and in the third you will have yeah. So, you just have minus x2, that is minus 2 minus 0 is just minus 2. So, that is also not available. So, you will just have A2 transpose, right. So, yeah, A2 you know is 1 comma 1. So, you will just have 1 1 1 1, which is actually a singular matrix. So, if you check the matrix A, right. So, the rank of that matrix is 2, which is actually n in this case, right, but nevertheless we have actually got a singular matrix because I mean for 2 of the constraints that we have, the inequality constraints, right. So, this inequality that we have here, right. So, ai transpose x minus bi plus mu I by 2 gamma. So, that was not holding, it was actually less than 0, right. So, you will have to remove those particular rows, okay, or from A, or if you are removing from A transpose, you will have to remove the columns, right. So, yeah, so the Hessian, if you have only inequality constraints, right. So, that will be, I mean some subset of columns from A transpose, right. So, So, you can call that B if you understand that better. Okay. And yeah, so in this case let us say B transpose of 3 comma 2, right. So, that will just be 1 1. Okay. So, because this column and this column do not satisfy the constraint Gi of x plus mu I by 2 gamma greater than or equal to 0, right. And similarly B of 3 comma 2 will be 1 1, right. So, you can see that B transpose B is singular. So, B transpose V will be non singular if, okay, yeah, B transpose B is non singular if rank of B equal to n. Okay. So, that is possible. So, for example, if you had given minus 2 comma minus 1, right. So, if x equal to minus 2 minus 1 and mu is 0 0 0, right. So, you can see that yeah, for A1 you have 2 minus 1 which is greater than or equal to 0, right. So, A1 transpose x minus B1 equal to 1 which is greater than 0. A2 transpose x minus B2 is minus 2 minus 1 is minus 3, minus 3 minus 1 is minus 4. So, that is less than 0, okay. And A3 transpose x minus B3 is 2 no sorry, it is 1 minus 0 is 1. So, that is greater than 0, okay. So, yeah, you have 2 columns. So, you have B transpose of minus 2 minus 1 will actually be minus 1 1 and 0 minus 1, right. So, you can see that rank of this is 2, right. So, B transpose B was actually non singular. So, if you can recall that when we used minus 2 minus 1, B transpose B was non singular. When we use 3 comma 2, B transpose B was singular, right. So, yeah, when you have inequality constraints, yeah, it turns out that the even for non trivial problems we can have non singular Hessian, right, but that has to happen for every single point that goes in the trajectory, right. So, we have a trajectory of points before we converge to the answer, right. So, for every point in the trajectory we need B transpose B to be non singular, only then we will have the particular the method to converge to the right answer, converge to the solution, right. So, yeah, that is yeah, we can construct problems where that happens, okay, but for most of the given problems you will see that these constraints are not going to be satisfied, right. So, if you even if in between you have one point where the Hessian becomes singular, your problem actually cannot be solved using augmented Lagrangian method, right. So, because the Hessian has actually become singular and that happens almost every time. So, when you have equality constraints only, then it happens every time, yeah, except for the trivial case. And for inequality constraints, yeah, you might have many points in the trajectory where yeah, the Hessian could be singular, right. So, that is the reason we actually avoid using augmented Lagrangian method to solve for the linear programming problem. Actually, it is the same for the quadratic penalty method as well. So, if you check the Hessian of the quadratic penalty method, right. So, yeah, here it is, okay. So, you can see that the Hessian of f is 0, Hessian of gi's are 0, and you will only have the del gi transpose as we had for the augmented Lagrangian method, right. So, yeah, this is for inequality constraints. So, yeah, when you have both, yeah, this is what if I had written down the Hessian, right. Okay, yeah, I have written down the Hessian for equality constraints, right. So, of course, you will have this one alone, you will not have del 2 f and del 2 h j, and similarly here you will not have del 2 f and del 2 gi, but you will only have del gi into del gi transpose. I think that kind of shows that why we actually avoid using these two methods, augmented Lagrangian method and quadratic penalty method for nonlinear programming problems. So, sorry, for linear programming problems. Of course, for nonlinear programming problems, these methods work well from the examples that we have actually given, right. So, in the next week we will start with linear programming problems and the methods related to linear programming problems. Thank you.